Okay, we're in chapter 18, section 3, entitled Reactions of Ethers. And what we're going to look at is ethers undergoing cleavage under acidic conditions. Alright, so let's take a generic look at this, and just to get an idea of what's happening. First off, we have an ether here on the left. Alright, this is the general structure of an ether. It can be essentially any ether. And we're going to subject this to a strong acid. And what's going to happen is this is going to break apart into an alcohol and an alkyl halide. So this is an overall process that we're looking at. We're going from an ether to an alcohol to an alkyl halide. Now, we have to pay close attention to the features associated with each ether. So let's just take a look at this ether that we have here. This will be isopropyl methyl ether. And the one thing I'd like to begin with is to understand the order. Folks, this is a secondary carbon. Why? Because it has two carbons attached to it. And of course, this is a methyl group. Now, why is that important? Because it's the nature of those groups that's going to determine the alcohol and the alkyl halide respectively. So I have this generic rule here. It says that the more hindered component becomes the product alcohol, and that the less hindered component becomes the product alkyl halide. Now, as you know in organic chemistry, to understand how these things occur, we'll always look at a mechanism. So let's go ahead and move to the bottom of page 105 and talk about the actual mechanism that's taking place. So here's the ether, and here's a strong acid. This should be hydrogen iodide. The first step in this process is protonation. Okay. Now, what does protonation do? Protonation is going to turn this methoxy portion into a good leaving group. So the first step is we add a proton to the sp3 oxygen. Now, once that happens, we've liberated an iodide. Okay, and so the iodide anion is going to function as a nucleophile. Whereas the protonated ether, in effect, is an electrophile. And you've come to know this process as an SN2 reaction. So why does the iodide attack here and not there? Because, as we said moments ago, it's the less hindered component that becomes a product halide. Okay? So this specific reaction applies if we have a secondary, and in this case a methyl alkyl component as part of the ether. But we have to work other examples to make sure that we understand the full scope of this. So let's move over to page 106 and take up another example. So I'm looking at the top of page 106. This is sample problem 18.09. Now here we have a slightly different scenario, but not that different. Let's read the directions. It says predict the major products. Notice it's plural. That means we're going to get an alcohol and an alkyl halide for the following ether cleavage reaction. And then I go on and add that the ether possesses both the primary and secondary alkyl components. So as you can see, this is the secondary component of the ether because this carbon has two carbons attached to it directly. And obviously this is the primary component because this carbon has only one carbon attached directly to it. So what's going to happen here? If we use the reaction at the bottom of page 105, as a model for what's taking place, then we should be able to predict with great clarity what's going to transpire. So the more hindered component, which is this side, is going to become what? The product alcohol. Okay? So let me go ahead and sketch those nuclei in. There's the oxygen, and there's the proton. This became the alcohol, in this case isopropyl alcohol. And the other side will be ethyl bromide, because bromine in this case would function as the nucleophile. So it's that simple. Now, I want you to pay close attention, though, to other examples that we're going to have later in this chapter, because it can get a little more complicated than that. But for now, that's what we're looking at. Now, before we move into more complex systems, I'd like to talk about another type of reaction involving ethers. And this is called the Claisen rearrangement. Claisen was quite the chemist. But what we have here on the left-hand side is a compound that is an ether. Notice we have a carbon-oxygen-carbon bond, so it's an ether. And this group you're looking at here is called an allyl group. Right? This is an allyl group. So this is allyl phenyl ether. Now, what's going to happen is we're going to subject this reaction to extremely high temperature. In fact, we're going to heat it up all the way to 250 degrees. That's really hot, okay? And so what we're going to see is a rearrangement. Now, when I say rearrangement, take notice that the molecular formula of allyl phenyl ether is C9H10O. Look at the product. The product is orthoallylphenol. What do you notice about the molecular formulas? They're the same. Okay? In other words, here we have C9H10O, and here's C9H10O. So it's just a rearrangement. Now, you might ask yourself, what's the driving force behind this reaction? Why would it want to go from here to here? As it turns out, this product on the right, the phenol, is actually thermodynamically more stable. Well, how did it happen? The process happens intramolecularly. It's an intramolecular rearrangement. Okay, let me explain that. But let me write that word down. Intra, I-N-T-R-A, molecular rearrangement. So the atoms are scrambling about, but it's going to result in a much more stable compound. So what I've done is I've taken allyl phenyl ether, okay, the compound you see here, and I put the allyl group in a different orientation. Now you may notice in brackets I said that the mechanism involves a 6-membered transition state. Okay? And what do I mean by that? Here's what I mean by that. If you started numbering here or really anywhere, 1, 2, 3, 4, 5, 6, you would see that there's 6 atoms involved in this transition state. In other words, TS marks the transition state. Now, what's going to happen overall? The pi bond you see as part of the aromatic system, okay, is going to migrate and form a sigma bond here. Similarly, this pi bond will migrate and form a pi bond there. And the sigma bond will actually break and produce a pi bond here. So what do we get? This is what we get as an intermediate. Okay? This is a classic intermediate. Now, this intermediate, though, cannot be isolated. One thing you may notice about this intermediate is that it's not aromatic. Okay? It's not aromatic. It doesn't have the 4 features associated with aromaticity. And at a glance, you can tell that it's not conjugated all the way around. Furthermore, that carbon that I'm pointing at is sp3, so that means there's no p orbital. So this simply undergoes a process known as tautomerization. And since this is an effective ketone, okay, this would be the keto intermediate, all right? Or you could call it a ketone intermediate. And over here we have an OH bonded to a double bond. What was that known as? This is known as an enol. So this is the first time that you've seen the keto go to the enol. You're used to seeing the enol go to the keto. Well, why would it be that way? Because this is what? This is aromatic. And because it's more aromatic, it's stable. That's why I have the equilibrium arrow exaggerated to the right. So you can see in this case that the enol form is dominant. Now, let's see if we can work one of these on our own. Move down to the bottom of page 106, sample problem 18.10. It says, predict the structure for the following Claisen rearrangement. Now, the way I suggest that you go about this is you make an illustration of the transition state. This is, how do we do that? Here's how you do that. What you want to do is rotate, okay, this particular allele group so that the pi bond is pointing down. And then we'll use the same set of curved arrows to predict the intermediate, and then we'll finish the product. Okay, so here's how we do that. I'm sketching my aromatic ring. We're leaving it intact. Okay. And notice now I'm going to move down, okay, because I rotated this pi bond down. Now the stereochemistry about this double bond is trans, so we'll keep it trans. And what's kind of important here is that you have the pi bond on this side if you want to use the same set of curved arrows that we did above. Then we draw another pi bond in, another pi bond in. I encourage you not to use the aromatic sectet, okay, as a circle when you do these. You want to sketch these, okay, actually using alternating pi bonds. Okay, now what is this thing known as? This is our transition state, right? Now it's not essential that you do this, but I do recommend it. It's just going to allow you to predict with greater precision where the atoms end up. So I'm going to put a dotted line here to indicate that we have that six-membered transition state. And then I'm going to use the same set of curved arrows that we did here. So let's place this pi bond in between this carbon of the aromatic ring and that carbon of the side chain. Subsequently, I'm going to place this pi bond here, and then I'm going to break a sigma bond by placing this pair of electrons there. Okay? So follow the head of the curved arrow that tells you where the electrons are going. Looks a little bit different on OWL, because there you actually have to connect the bonds to the atoms. But here I'm showing you where the bonds actually go relative to the other bonds. Now by virtue of doing that, that's going to give us a tautomer. So we're not quite done. So let's just follow those three curved arrows to see what this leads us to. There's our six-membered ring. This pi bond, still there. Now we have a doubly bonded oxygen. Okay. Here's the new sigma bond that you've established. There's that methyl group out to the side. Here's also a sigma bond, but we now have a pi bond as part of that group there. Now it's tempting to stop there, but you know that we don't stop there because this form is a keto form. In the Claisen rearrangement, the keto form is not the most stable. So what do? You have to undergo tautomerization. Now tautomerization simply means that the proton is being scrambled about. Okay? So let's go ahead and sketch the proton in here, in that sp3 carbon, and it helps us recognize, okay, that it's going to be picked up by this oxygen, and this pair of electrons will collapse inside to reestablish aromaticity. So I've kind of run out of space. Let me just go up like that. And again, you can see what's going on. Okay? What's happening here, simply put, this pi bond is going to grab onto that proton, and this pair of electrons here will collapse, reestablishing aromaticity. So this equilibrium lies very much, okay, to the right, towards the enol form. Now the enol form is always characterized by having an OH group somewhere. So there's your OH group. Okay? And the pi bonds that were always there, we're leaving them as is. And there's the new established pi bond. And now we can simply sketch in however we want, okay, that side chain. Notice I've kind of turned that around, but it's okay. So this is your final product in the overall reaction. Let me put a box around it just to remind ourselves that it's the final product. A faint red box here. Okay. And just to keep track of what's going on, this is the enol form. The enol tautomer will always be the dominant in the Claisen rearrangement. Alright. So that does it for the Claisen rearrangement. Let's talk about other reactions involving ethers. At the very beginning of this chapter, I talked about, ever so briefly, epoxides. Now, epoxides, okay, are examples of cyclic ethers, and specifically an epoxide is a three-membered ring. So here's a generic example of an epoxide. All right. So how do you make an epoxide? Fundamentally, there's two ways. But really the best way and the simplest way is by taking an alkene and a per acid. We'll see a specific example in a moment. And they provide an epoxide and a carboxylic acid. You may notice the per acid is called per acid because there's two oxygens here, two sp3 oxygens. And it's been proven by isotopic labeling that it's actually this oxygen. Let me label that 18. Okay, let's suppose you had oxygen 18. Where does the oxygen 18 end up? It ends up in the product. Okay. In other words, that oxygen stays behind, and the carboxylic acid is this oxygen that gets transferred. Okay. Now we could go through all that in great detail, but just bear in mind this is just a transfer of an oxygen to a double bond. We learned this back in chapter 9. Here's one example. Again, this goes back to chapter 9. A specific example whereby we're using a cycloalkene, in this case cycloheptene, and here's our per acid. This is meta-chloroperoxybenzoic acid, MCPBA. And what happens? We produce an epoxide between this carbon. Our final result will be 1,2-epoxy cycloheptene. Now, one thing I want you to keep in mind, okay, for what it's worth, is that the hydrogens, okay, are going to be cis one another, right, on the same side. And you can tell we have two wedges here to indicate that the oxygen's above the plane. So this is your organic product. This is the reason we did the reaction. This is the organic product. Over here we have the byproduct. Now the byproduct is very valuable. Okay, this is meta-chlorobenzoic acid. But it can be converted back into meta-chloroperoxybenzoic acid. So it's not like we're going to lose that compound. We're going to keep it and use it for other reasons. Okay, so keep that in mind, this reaction. Let's look at another approach. This is another one we saw back in Organic 1. Okay, this whole page really is a review of Organic 1. But it involves two steps. This was one step, this is two steps. And how does this work? Here we're using an alkene, like we always do, but we have a halogen and water. Water turns out to be a pretty good nucleophile, therefore it ends up being part of the product. And this is called a halohydrin. You may remember this from Organic 1. Halo means we have a halogen. Hydrin means we have an OH. Okay? So this is step 1 in the overall reaction. Step 1. You can actually isolate the halohydrin. But if we want to make an epoxide, we need one more step. Okay? So this would be step 2. Step 2, we're actually going to remove a proton with a strong base. Alright? And let me kind of show you that. What's going to happen is you're going to remove that proton using a strong base, and we're going to generate alkoxide. Right? So the strong base removes that proton. Let me highlight that proton because we're going to lose that, okay, to the hydroxide anion. And so that's going to give us, as I just said, an alkoxide intermediate. The alkoxide intermediate has this generic structure whereby we retain the stereochemical integrity of these sp3 carbons, but now we have a negatively charged oxygen. And over here, again, we have a halogen. Folks, the halogen cannot be fluorine. It's limited to bromine and chlorine, or it could even be iodine. Okay? So this is your alkoxide intermediate. Now, provided this system is very dilute, any one of the 3 lone pairs on this oxygen, okay, can collide with the adjacent sp3 carbon and displace, in this case, the halogen, which functions as a leaving group. And by virtue of doing that, you end up with an epoxide. Okay? Do I remember what this reaction is called? This intramolecular reaction in step 2? It's an SN2. Okay? This is an SN2 reaction. The distinction here is an intramolecular SN2 reaction. Okay? Alright. Now, that's a generic example. Let's take a look at a specific example. Here we have an alkene, in this case cis-2-butene. We have a halogen, bromine, we have water. And so, by virtue of doing that reaction, we end up with our halohydrin here, that we can actually call it a bromohydrin. A bromohydrin. Why bromohydrin? Because we have bromine, and we have the OH bonded to an sp3 carbon. So again, you could actually isolate this product, purify it if you wanted to. This is step 1. Now, what's going to happen next? You're going to take your bromohydrin and subject it to sodium hydroxide and water. So we have an aqueous solution here. You're going to be refluxing it. Now, one thing I like to impress upon you, and this is pretty important, is the stereochemistry. Notice over here on the left that the methyls are cis one another, as are the hydrogens. But what do you notice about the methyls in your epoxide? They're still cis, right? They're still cis. So keep that in mind, that if you start with a cis alkene, you're going to get a cis epoxide, right? Technically, this would be a meso compound because there's a mirror plane that runs right down through here. But that's something you want to be mindful of when you do a specific example. Alright. So let's just take a look at another example. And this one's going to be somewhat analogous to the one we just did. The only thing different here is what? I have trans-2-butene. Okay? So let me show you the best way to go about that so that you'll always get the proper stereochemistry. We know that we're going to make an epoxide, right, between this carbon and that carbon because we see the bromohydrin conditions and then we see the cyclization conditions. But the question is, what is the stereochemistry going to look like? How do we get the right stereochemistry there? Here's how you do that. let me suggest that you draw everything that you see on the left minus the pi bond. Okay? So I'm sketching my two carbons. Now I'm going to place wedges and dashes, okay, on there, just like I see on the left. No genuine modifications whatsoever. We haven't changed anything about that. Nor have we changed the atoms. Look, there's still a hydrogen on that dash. There's still a methyl group on this wedge. There's still a methyl group on that dash. And there's still a hydrogen on this wedge. But just ask yourself, what happened here? Well, using up the example above, we put a bromine, okay, on one of the carbons, and we put an OH on the other. You say, well, which ones? Well, really both, okay? Half the time you get the OH here, and half the time you get the Br there. But you only have to draw one of these. So let's just keep this simple, okay? I'm going to go ahead and put the OH there, okay? I pointed it up, I could have pointed it down. I could have put the OH on that carbon. I could have pointed it up or down. Doesn't matter. But once I've done that, I need to come over here and put the bromine in this spot. Okay? So this is actually the bromohydrin intermediate showing the proper stereochemistry simply by placing an OH, okay, above the plane and a Br below the plane, or reversing it. Now if you're thinking deeply about the stereochemistry, you need not be too concerned about it. Okay, but let's just keep going. So what's going to happen next? If I stayed it up here, you're going to lose that proton. Okay, this hydrogen is going to be gone, and this oxygen is going to come in here and collide with this carbon and displace that bromine, making the three-membered ring. So let's just use this pragmatic approach. Okay, they're the two carbons, and I'm going to go ahead and make my epoxide ring now. Okay, because we know that ring closure is going to take place. And where we formerly had a hydrogen on the dash, we still do. Where we formerly had a methyl group on a wedge, guess what, we still do. Where we formerly had a methyl group on a dash, we still do. And where we formerly had a hydrogen on a wedge, we still do. Nothing's changed about that. Okay? Nothing's changed about that. So not only have you drawn out the proper structure, but you've also addressed the stereochemistry. So let's just remind ourselves one more time. Here we have the transalkene, okay, because the methyls are trans one another. Well, what's the relationship between the methyls here? This one is on a wedge, that one's on a dash. You retain that trans stereochemistry, okay? Nothing's changed there. Now this reaction here also produces a mirror image, okay? This is one of the enantiomers, alright? So 50% of your product is that, and the other 50% is its mirror image, okay? But you only have to draw one of these, okay? You need not sketch both of the enantiomers, alright? So I'm going to write in up here though, just to kind of remind ourselves of this, that we also get the mirror image. You get the non-superimposable mirror image, enantiomer. Okay? So this ends up being, okay, this ends up being racemic. Y'all remember what racemic meant? It meant you end up with a optical rotation of 0, 50% of each enantiomer. So here, alpha, okay, alpha equals 0 degrees C. And if you want to put that in brackets, you can as well. Alpha D equals 0 degrees C. So this is optically inactive when you do the overall reaction. Okay, so that's another way to make an epoxide. Now, what do you do with epoxides? What good are they? Turns out epoxides are really versatile. You do all kind of good things with them. If you've ever bought those glues, okay, that they sell that come in 2 tubes together, and you squeeze them out and you make this real strong adhesive, one of them has an epoxide in it, so you make an epoxy resins. So here let's talk about the reactions that epoxide would undergo. And the reaction they undergo, you probably can imagine, is ring opening. Well, why would they want to open up? Okay. Well, look at it. What's the hybridization of all the atoms in this ring? They're all sp3, right? What's the preferential bond angle for sp3? 109.5. What are the angles here? The interior angle is about 60 degrees for each because this is a triangle. So there's a lot of angle strain here, okay? So if I ask you what kind of strain does the epoxide have? Okay. The dominant strain is angle strain. The dominant strain is angle strain. Now there's two sets of conditions that you can subject an epoxide to. One's acidic conditions, okay, which is a little harder to understand than basic conditions. Let's go through a generic mechanism and then we'll look at a specific example in just a moment. So, we're going to take an epoxide and subject it to a Bronsted acid, okay? And the first step in these is always the same thing. You're going to protonate that oxygen. And when you do that, it's like you have a good leaving group, okay? This ring is going to be especially suited for opening. So we start with the epoxide. The next thing we do is we protonate, okay? It's called protonation. Now keep in mind, this is a Bronsted-Lowry acid, and this is what? A catalyst. This is a catalyst. You only need a little bit of this. And so at the very end, the catalyst is going to have to come back. The overall result is that you get a 1,2-diol, which we also said is referred to as a glycol. Okay. You may remember back in Organic 1 that we also referred to these as vicinal diols. Okay, vicinal means the OHs are side by side. Well, how does it work? Like I said, the first step is protonation, and that's going to make this ring especially reactive. Once you've protonated that oxygen on the epoxide ring system, a nucleophile can come along. It can attack here or there, really 50-50 here or there, and then you're going to get the ring opening. So it's at this stage that we have the ring opening. Alright? This is where that ring is popping open. It's the ring opening. And again, that's an SN2 reaction. So what's the leaving group? The leaving group here is simply this bond breaking. So it doesn't leave the intermediate, but the bond leaves this carbon. So we would still call it a leaving group. Alright, once that's happened, like we said, you have to get your catalyst back. But bear in mind, there's plenty of water in this system. And so water can come along and pick up either one of these protons, okay, to once again regenerate the catalyst. Alright, so let me read aloud what I have here. Under acidic conditions, the protonated form of the epoxide is a common intermediate. Okay? In other words, this is a very common intermediate you're going to see throughout the next couple of pages. The nucleophile will only attack via SN2 if the electrophilic carbon is a methylene and sometimes secondary. SN1 will occur with secondary and tertiary carbons. Okay, so suddenly things have gotten pretty complicated. But we don't have to reinvent the wheel because you have this back in Organic 1. So we're going to look at this a little more closely by looking at some profound examples. Now, let's do this. Because this is SN2, alright, there is an inversion that takes place here. There is an inversion. Now, case in point. On the bottom of page 108, I have epoxide. And again, this is a cis epoxide. You can tell that because the hydrogens are both on dashes. You can see that the oxygen is above the plane. Stereochemistry is R and S. Alright. So this is a meso epoxide as well. Okay? Meso means that there's a mirror plane right through there. The top half is the mirror image of the bottom half. So what do we expect? Folks, when you pop open an epoxide, you get a diol, or more specifically, you get a glycol. But notice the stereochemistry now. We have retention at one carbon, but we have inversion of the other. So in this case, we don't end up with a cis diol, we end up with a trans diol. So that's what's important for this reaction at the bottom of page 108. Now it always helps to look at other examples. So let's flip over to page 109. On page 109, move it up a little bit. I've given you an example whereby we're going to use a trans epoxide. And what I'd like to do is kind of walk you through this overall process so you can see firsthand what's happening. Alright, so let's read the directions first. It says, predict the structure of the product diol showing the correct stereochemistry. Alright. Now the correct stereochemistry, if you're concerned about that, don't be. What you need to understand is simply how to follow the rules. So let's give this a shot. I think we can do it. The first step is protonation, right? Just so you keep in mind what's going on. Here's our Bronsted-Lowry acid. Another hydronium ion. The oxygen has a couple lone pairs on it. What's going to happen? We're going to pick up a proton from the Bronsted-Lowry catalyst. That's going to lead us to this protonated intermediate. Now what do you know about this intermediate now? This is especially reactive. Why? Because now you've got a good leaving group. You keep in mind that the leaving group here doesn't depart from the parent molecule. Instead, we're simply going to break a bond. What's the next step? The next step is going to be nucleophilic attack by water. Water can function as the nucleophile because guess what? It has lone pairs. Now where's it going to go? Is it going to go here? Or is it going to go there? It'll go both places. It'll go here 50% of the time, and it'll go there 50% of the time. So like I said on page 108, we only have to show, we only have to show one of the scenarios. So let me just have that nucleophile attacking, how about here? Okay? Here or there. Well, if it attacks there underneath on the least inner side, the leaving group is just pair of electrons. It's going to break. And what's that going to do? That's going to provide you with your next intermediate. Okay? Now the next intermediate will simply be the protonated form of diol. Well, let's go ahead and sketch it, okay, the final product, because the last step is pretty trivial. Okay, here we go. Alright, take a look here. The methyl group that's on a wedge on the left-hand side is still there on a wedge on the left-hand side. This bond broke, so that means that this OH group now, okay, is here. On the other side, notice how that the methyl group is behind the flame and the hydrogen is facing you. What's going to happen when that nucleophile attacks? All that's going to happen, okay, is there's a subtle inversion, almost too easy to understand, okay? That methyl group's going to go up slightly because this carbon now has got a little more freedom. So there's that methyl group. And then hydrogen also is going to retain a wedge. So yeah, this is an inversion by simply coming underneath. You're not switching things out with wedges and dashes. You're not doing that. And ultimately the OH will be there. Okay? Now let's take a look at the stereochemistry just so we understand what took place. On the left-hand carbon, this is a chiral carbon. This is the high priority group, right? So this would be 1. This would be 2. This would be 3. So 1, 2, 3. We're going clockwise. This is R. On the other side, we have the OH group here, which is number 1. This is number 2, and the methyl group is behind the plane. But because it's behind the plane, this is S. So what is this known as? Okay. When you get the R on one half and S on the other half, this is meso. So folks, trans epoxides, if they're symmetrical, give you mesodiols. Let me just write that in. So the mesodiol. Okay. But again, this has to be symmetrical. So let me put a line here. Okay, put that through there. Notice the left-hand half, the right-hand half, okay, both contain the same elements. If you have that, the trans epoxide provides you with the mesodiol. So you may have to dwell on this one a bit to understand it fully. Okay, so had I had the nucleophile attack here instead, what would that have meant? It meant you would have also had 50% of this same product, but since meso, folks, contains chiral carbons but optically inactive, you could not tell them apart. Alright. Now let's move to the middle of page 109. And here we're going to talk about epoxide opening, only we're going to have it in a different type of reaction. As opposed to using aqueous conditions, we're going to use hydrogen chloride, okay, in ether. This is not, okay, hydrochloric acid. This is hydrogen chloride. It's a much stronger acid when it's in ether. So the nucleophile here is not going to be water, it's going to be chloride. So I think I made note of that. This is epoxide opening under what? Anhydrous acidic conditions. Okay? So those are the anhydrous acidic conditions. The reason you know it's anhydrous is because there's no mention of water. You don't see H2O written here, okay? You don't. You don't see the symbol AQ. You don't. So that guarantees that these conditions are anhydrous. Now let me give you a little bit of warning. It's incumbent upon you to recognize the order of each carbon before you do these. So this is a specific example, okay? Take a look at this carbon, that one. How many carbons do you see attached directly to it? You see 1, 2. So this is a secondary carbon. That's important to do this. Look at that carbon, part of a methylene. How many carbons are attached directly to it? 1. So this is a primary carbon. Okay? Now why is that integral? Because that's going to determine where the OH ends up and where the Cl ends up. So we need to figure this one out. And I'm going to show you that in the mechanism in a moment. Alright. What looks like is happening, it looks like what's happening here is that the Cl is ending up with the primary carbon more often, right? And that the Cl ends up in the secondary carbon far less often. So 90% of the time, the chlorine bonds to the less-centered carbon because it's a nucleophile, and about 10% of the time the chlorine bonds to the secondary carbon. So we can say with conviction that this is the major product, right? There's no doubt about it, because there's more of it. A lot more. This will be our minor product. Well, that's fine, okay? But it's probably better, rather than say major and minor, but to characterize exactly what they are. Folks, the major product in this case is this is the SN2 product, because it happens by way of an SN2 mechanism. And you know that because the nucleophile attacked the less-centered carbon. But what's SN2 sometimes in competition with? SN1. So this is the SN1 product. Why? Because the nucleophile went to the higher order carbon. So study this reaction to get a great feel for what's going on, because the mechanisms are very different. Now let's move to the bottom of page 109 and look at another example. This one that's already been worked out, but it uses the above as a model. Now what I'd like to do here is kind of walk you through the mechanism here. But what was the first thing I told you needed to do? You need to address the order of these carbons. Alright? So what I'm going to do is I'm going to put some arrows to those carbons. And we're going to figure out their order. How many carbons is this one bonded directly to? There's one, and there's one. So the answer is 2, the secondary carbon. And methylenes are always primary carbons. So that's the same scenario we have here. Well, how does this work? What's the first step? Folks, the first step is the same as the one you saw moments ago. It's going to be protonation of the oxygen of the epoxide ring system. That's the first step. Chloride has a full octet, but it can function as what now? A nucleophile. Where is the chloride likely to attack? Well, it's going to attack the carbon that has a good leaving group. Is that going to be that one? Or is it going to be that one? Well, you know that with SN2 reactions, the nucleophile always does what? Attacks the least hindered spot. So folks, the chloride will attack there majority of the time. Why? Because it's the least hindered spot. It's the primary carbon. So those two curved arrows that I just drew, what kind of mechanism is that? That's the SN2 mechanism. So which product did they result in? Which product did we get as a result of that? Is it the one here on the left or the one on the right? A quick glance can tell you that the chlorine attacked the methylene, so there's a chlorine attached to a methylene. So this is our major product. And obviously that's the minor product. Okay. Now, how did that chloride get in there? By what mechanism? SN2. Well, how did that chloride get there? Did it get there by this chloride attacking there? Nope, not directly. In this case, what had to happen first was the ring opened up and then the chloride came in. So this is an SN1. So what I'd like you to do between now and your third exam, is read this explanation. Okay? Because it gives you specific example. It lines up with these specific examples that we just described at the bottom of page 109. It's good reactions to know. Okay, let's flip over to page 110. I'm going to change things up a little bit. Folks, here I have another specific example whereby we have tertiary and primary carbons. So I'm showing you what's going on. First off, this is a tertiary carbon. Why? Because that carbon that I have the arrow pointing to has 1, 2, 3 carbons attached to it. This is primary. Methylene is always primary. And you already know what's going to happen. Okay? You already know. We're going to open up this ring system. One of the carbons is going to be an OH, either that one or that one. And one of the other carbons is going to have a chlorine, either that one or that one. So you already know what the products look like. They turn out to be constitutional isomers. But let's take a look at these percentages, because they're different than the last one. This is 40%. This is 60%. Okay? So what does that mean? That means that this is the minor product, although not as minor as the previous one, and this is the major product. Okay? So how did that happen? Folks, how does chlorine get to methylenes? Right? Same way it did before, by way of an SN2 reaction. So that's the SN2 product. How did the chlorine get to this carbon, the tertiary carbon? The same way it did in the previous page, by an SN1 mechanism. Okay? The distinction here was on the bottom of page 109. We didn't have a tertiary carbon, primary carbon. There we had a secondary carbon and a primary carbon. So you want to compare these two to understand this in full scope. Now, let's try a model example. Look at sample problem 18.14 in the middle of page 110. Here, we're asked to predict the major alohydrin. It's so tempting to go straight to the answer, okay, but I don't want you to do that just yet. Let's find out what's going on. Folks, what's the order of this carbon? Let's look. It has 1, 2, 3 carbons, so it's tertiary. What's the order of that carbon? It's got 1 carbon attached. Oh, it's a methylene. We've seen that a bunch of times. So the above model, the one right here, gives us the answer. When you have a case with a tertiary carbon and a primary carbon, you're going to get mostly SN1, okay? Because it's going to pop open and give you a tertiary carbocation. So in this case, our major product is the one on the right. This is our major product. And this one here, with the OH bonded to the tertiary carbon, is going to be the minor product. Let's remind ourselves of the mechanism. Folks, if the nucleophile goes to the less hindered carbon, it's always going to be SN2. If the nucleophile ends up at the more hindered carbon, it's going to be SN1. And as before, here's our explanation. Okay? So read over that so you can get a feel for exactly how this works. Okay, let's go ahead and stop there. And then we'll come back and finish up this chapter. The remaining material is much easier to understand than what we just went over.